Hey, what's up, y'all? We're going to look at section 5.5. So let me go ahead and set up my notebook paper real quick. And I'm going to start doing some videos here. And when I do the videos, I'm not going to do page numbers because the page numbers could be off when I use these maybe in the future or something like that. So hopefully that's something you've already discussed, you'll soon discuss, or you'll just make sure it's correct. So this is section 5.5. And we're going to call it theorems about polynomial equations. Okay, theorems about polynomial equations. And even though I'm saving this video, I'm not going to improve my handwriting. It just is what it is. It just is what it is. So theorems are ideas about polynomial equations. A polynomial, polynomial could, let me give you an example of one. Let's look at polynomial equation. 15x cubed minus 32x squared plus 3x plus 2. Let's set it equal to 0. Oftentimes we'll set equations equal to 0, and if they're not equal to 0, we make them equal to 0 by over the line changing the signing, all of the stuff there. So here's our first polynomial equation. This is a polynomial because all of the exponents are whole numbers or just no x there at all. And yeah, that's the main thing we look for. It's in standard form. X to the third, x squared, x, and then that is our constant term at the end there. Okay, so our first theorem is the rational root theorem. The rational root theorem. Rational root theorem. So this is saying that if you have roots of an equation that are rational, this is going to help you find them. Now sometimes the roots, let me, I guess, go back a little bit. A root is a solution. Okay, so if there's a value of x that will work in this equation to make this come out to 0, that is a root of the equation. It's just another word for solution. We also sometimes call it a 0. Okay, and that's a 0 spelled out. Not the number 0, but a 0 is when it equals 0. So a root, a 0, a solution, they all mean the same thing. And rational means that it is not a square root. There's no I. I think those are the two things we'd be looking for here. So a rational root theorem is going to find those solutions, not the ones with square roots or i's, but the rational ones, the ones that could be written like a regular fraction. Okay, and what the rational root theorem says, and let me get a couple different colors here. Take the number at the end, the 2, and we're going to put that in the numerator. And take the number at the beginning. Let me get another color here. I've got a nice green. And put that in the denominator. And then list their factors after them. So what are all the numbers that go into 2? Well, that's pretty easy, just a 1. And all the numbers that go into 15, well, 15, 5, 3, and 1. So the rational root theorem says that all of the solutions that are fractions look like one of these pairs, one of these in the numerator and one of those in the denominator, and a problem might ask you to list all of those out. So we can go ahead and do that. Let's start with 2 over 15. Oops, should I use the colors? Okay, so I'm going to have 2 over each of these. So 2, 2, 2, 2, and then 15, 5, 3, and 1. Okay, and I have some other possibles. I could use the 1 in the numerator there. So 1, I'm going to have to go to the next one. I'm going to run out of room. Okay, so of the numbers of the possible solutions to this equation, if it's a rational number, it has to be one of these. So we'll have 8 different numbers to choose from, and they could be positive or negative as well. Let me go ahead and note that. So these could be positive or negative. That could be positive or negative. That could be positive or negative. That, yes, all of these could be positive or negative. There we go. Okay, so that's what the rational root theorem says. Now we can graph this to see which ones are actually correct. So let's go ahead and graph this. I have 15x cubed minus 32x squared plus 3x plus 2. And if you didn't have a graphing calculator to do this, you could just start plugging numbers in here. It'd just be kind of tedious. Take 2/15, put it in there for x, multiply it all out, do all the stuff, and see if it comes out to 0. But I probably want to use a calculator for that anyway, so might as well just get out the horsepower here. So there's my equation. Let's go ahead and graph it. Okay, this is in standard view. It's 10 by 10 by 10 by 10. But look at my answers. The biggest answer I have here, I think, is 1. No, 2. The biggest answer I have here is 2, and you can see that all the numbers are kind of small. So let's zoom in a little bit. I'm going to use zoom decimal. Okay, there we go. And now we can start to get some of these solutions here. Hit the trace button. Hit the trace button. Now this solution right here looks like it is at 2, and let's go ahead and hit 2 and double check. 2 is a solution, okay, because 2 comes out to 0, so 2 is a root. So let me start with this. My solutions, well, are 2. We've got 2. Okay, what else could we have here? Well, I don't know. Right here, it looks like it's kind of close to 0. Not as close as that one right there. Maybe 1/3. And yes, 1/3 comes out to 0. Great, great, great. Okay, so 1/3. So positive 1/3 is another solution. And then I have a negative solution over there. I have a negative solution. Maybe negative 1/5. Negative 1/5. And let me see, that's, oh yes, that comes out to 0 as well. So negative 1/5 is correct. Okay, now I wouldn't have been able to guess that this was at negative 1/5 unless I had some helpful information up here. Okay, this gives me some way to narrow down what the possible solutions might be. So I was able to narrow it down, and when I put in the value, it gave me 0, so I knew it was a solution. So that's how we can use the rational root theorem to help us solve a problem. Okay, even if you can graph it and do all that, it's handy to have some other way to kind of narrow down those choices and get you there. When you use the solve function on the calculator, it's not always as precise. I would, if you want to be really precise, and what you can do, you can use synthetic division and divide by your solutions, and the remainder always comes out to 0. And so if you need to prove that this is a solution, that is how you would do it. Let's look at one other thing here today. The conjugate root theorem. The conjugate, the con, stole a jug, and then he ate it. Conjugate root theorem. Okay, the rational root theorem dealt with rational numbers. The conjugate root theorem deals with those other kinds of roots. It deals with irrational roots and complex roots. I guess I put the word roots there, but I put the roots there, or the word roots there as well. Whoops, ruse. Okay, so I have irrational roots and complex roots, and the conjugate root theorem deals with these kinds of roots. And what this says is that if you have a polynomial with rational coefficients, like if you don't see, like we do here, all the coefficients are rational numbers. In fact, they're whole numbers here. But if you have coefficients, if you want your coefficients to always be rational numbers, you have to have these kinds of roots in conjugate pairs. So if, let's go ahead, if you have a root of square root of 5, you need another root of negative square root of 5. Okay? And if you have a root of 1 plus square root of 2, you have to have another root of 1 minus the square root of 2. Okay, those have to come in pairs. So for complex roots, it's the same thing. If you have a complex root of 3i, let's say negative 3i this time, well, you have to have another root of 3i, and those will kind of cancel each other out. Okay, if you have a root of 3 plus 2i, you have to have a root of 3 minus 2i. Okay, so the conjugate root theorem says that if you have irrational complex roots, they have to appear in pairs, like that. Okay, let's look at a problem from this. So let's say, write, the problem says write a polynomial with rational coefficients. Okay, write a polynomial with rational coefficients with roots. Let me see what I got here. 4 and negative 2i. Okay, well, to do this, we need to say, well, wait a minute. I want rational coefficients, so I have to add another root here. I can't just have 4 and negative 2i. I also have to add on, and let me add it on with a different color. I also have to add on positive 2i. This is the conjugate. Okay, this is like that pair right there. Okay, you can always reference one of those pairs up there. Okay, so write a polynomial with rational coefficients with these 3 roots now. Okay, so let's go ahead and try this. To do this, I have 3 roots, so I'm going to use this form. My polynomial is going to be x minus, and x minus, and then plug in these 3 things. Okay, so 4, negative 2i, and 2i. Okay, and then we're going to multiply this out to get the polynomial in standard form. So let's always start by multiplying the conjugates together first. So we're going to multiply x. This is really x plus 2i, right? Minus negative becomes plus. So we're going to take x plus 2i times x minus 2i. And I'm going to copy this one down. And if you do that and you FOIL it out, remember the conjugate, you just have to floor it. So let me see. This is going to be x squared. And then the 2 in the middle will cancel out. And 2i times negative 2i. Well, 2i times negative 2i, that's going to be negative 4i squared. But then it's going to be plus 4. Okay, and you can FOIL those out. Just remember that I times I is I squared, and that will change the sign of your number. And you will get the same answer that I got there. Okay, let's continue here. Let's multiply these together, and I'm going to FOIL these. I'm going to do it in an order so that they are in the order I want them to be. So the inside next, negative 4 times x squared, negative 4x squared, because I want to write this in standard form. I want the cube first, and then the square. So between the middle and the outside, or the inside and the outside, the inside one was going to give me the standard form. So that's why I FIOL this time. X times 4 is plus 4x, and then negative 4 times 4 is negative 16. So a polynomial in standard form with rational coefficients, with the roots that they wanted, is there. Now I can double check this by graphing it. And of these up here, the only root I should see is the root at 4. I shouldn't see a root for negative 2i or 2i because those are complex. So let me go ahead and graph this, and I should see a solution at 4. So x cubed minus 4x squared plus 4x minus 16. I should see it come right here. Bam, there we go. So this is correct. I see one solution at 4. Maybe I could zoom standard just to be sure there's no funky business going on anywhere else. Oh, that's beautiful. I love it. Okay, so that is our solution. This is a polynomial with rational coefficients at with those roots.